Hi there, Mr. Sutton back with another exponential lesson. This one will be tackling graphs of exponential functions. We'll also be determining whether an exponential function is growth or decay. And the real-life payoff, we'll talk about the spread of a rumor. For your warm-up, go ahead and graph this function, y equals 1 times 2 to the x. And here's all the x values you should use, so figure out the y values and put some points on there. Alright, let's do the easy one first. So first power, this would be 1 times 2 to the first power. So just 2 to the first is 2. 2 to the second power is 4. And now let's do these other ones. So we've got 2 to the negative 1. We know that's really reciprocal, so 1/2. And then 2 to the 0, that's just 1. Anything to the 0 is 1, so we got 1 there. So we got negative 1, 1/2. We have 0, 1, 1 comma 2, 2 comma 4. And extrapolating that curve, there we go. There is our exponential function on a graph. So let's talk a little more about these exponential functions. What we've seen so far, that form that I gave you, is standard exponential form. That's when you have some number times a base to the x power. And what makes this an exponential function is that the x is in the exponent. So now the a is going to be our y-intercept. If you plug 0 in for the x, you'll have a times b to the 0, and b to the 0 is just 1, so you get a. So here we have an a value of 1 for this particular function. The b value is what we call the growth factor. This is what you multiply by each time with your exponential function. If your growth factor happens to be bigger than 1, so that you're multiplying by something bigger than 1 over and over again, then it is actually exponential growth. So this graph here is an example of growth. If, on the other hand, your b value is between 0 and 1, you've got decay. Here's a picture of what that looks like. If you're multiplying by a number that's like 1/2, it's a fraction, a positive fraction that's less than 1, you just get smaller and smaller and smaller. Now some of you might be wondering, well, why didn't I just say b is less than 1 for decay? We don't want our b value to be negative. It turns out growth factors can never be negative. And if you think about it, there's very good reasons for this. You're supposed to be able to plug in any x value to this part right here. So that means you need a number that you can raise to any exponent. Now negative numbers, if you raise them really just to even and odd exponents, you're going to just keep flipping all over the place, because a negative becomes negative when you have an odd power, and it becomes positive when you have an even power. So that alone is crazy. But it gets worse. If you plug in a fractional exponent so that you're taking like the square root of a negative number, that's just bad news. So no negative bases. Now exponential functions, you'll notice here that we're getting closer and closer to the x-axis, but we can't actually touch it or cross it. Same thing up here with growth. And this is because if you're raising a positive number, and we said b has to be positive, if you're raising a positive number to an exponent, multiplying it by itself, there's no way you're going to get a 0 out of that or a negative number. So exponential functions can't return negative values or 0. And we can go a little bit further and say that we have a horizontal asymptote at y equals 0, whether you have growth or decay. Let's do a real-life problem now. Let's say you start a rumor by telling people that there's going to be an assembly, and you start by telling 3 people this. And then every hour, each person who hears the rumor tells 3 more people. Make a graph of the number of people who are going to learn the rumor each hour. So not the total number of people who know the rumor, just the new people who are learning it each hour. So first off, we can tell from the b value here, which is greater than 0, that this is going to be a exponential growth function. So when you graph this, you should expect something that is increasing as you move to the right. So let's go ahead and make our table of x values and y values. And I usually do -1 through +2. I found that gives a good picture of an exponential function. And I know -1 doesn't really make sense here. You know, the number of people who knew the rumor an hour before you started it. So that's just kind of weird. But we'll put a value in there just so we can kind of direct where this function is going. So that'll be 3 to the -1, or 1/3. And then 3 to the 0 is 1. At the 0 hour, you are the only one who knows this crazy rumor. And then this will be 3 to the 1, which is 3, and 3 squared, which is 9. So we got -1, 1/3, 0, 1, 1, 3, and then 3 comma 9, or 2 comma 9. And there's our exponential function. Wow, look at how fast the number of people who think there's an assembly is growing. Here's another problem. Try this next one on your own. This one, we want you to complete the table and also state whether the function is growth or decay. We kind of did that for free last time, but this time they're requiring it. Notice also that your a value is no longer 1. So good luck. Give it a shot. All right, let's see what you came up with. Since our b value, the 1/3 here, is between 0 and 1, we know that this is going to be exponential decay. Let's make our table again with -1 through 2 for x values. So when we plug in -1, we're doing 1/3 to the -1. That's the reciprocal of 1/3, which is 3. So that's really 6 times 3, which is 18. 0 power now. 1/3 to the 0 is just 1, times 6 is 6. And this is the a value, 6 is the a value, so we should have a point that goes 0 comma whatever this number is. And now 1, we've got really 1/3 to the 1 is just 1/3. 6 times 1/3 is 2. And then the second power, this becomes 1/9. 6 times 1/9 is 6 over 9, or 2/3. Let's graph it out. -1 comma 18 all the way up here. And then 0 comma 6. Look at that drop. That's a big drop. And then 1 comma 2. And then 2 comma 2/3 is in this area. All right, draw that as best you can. Very hard to get the horizontal asymptote to look nice with this steep of a drop, but we make it work. For our wrap-up activity here, this is kind of a fun one. How do exponential functions compare to linear functions? In other words, how are they similar? How are they different? Take a couple minutes and see if you can come up with some similarities and differences. Some similarities I came up with. One of them is that these both have a y-intercept. For linears, it's the b value in mx plus b. For exponentials, it's an a value in ab to the x, but they both have that y-intercept that you can tell just by looking at the function. Another similarity is that they are both the result of repeating a certain operation over and over again. Whatever next value you're going to want, you can do the same operation and just keep getting the next value. Now for some differences. That repeated operation is different between the two of them. With linears, you have repeated addition. With exponentials, you have to repeatedly multiply. And the other huge difference is that the exponential function will eventually grow faster as you move forward and forward in time, and it will eventually decay slower. Linear functions, on the other hand, they only grow and decay at the same rate. Another difference, I guess, linears don't have any asymptotes, while exponentials always have a horizontal asymptote. So that's all for now. Till next time, this is Mr. Sutton signing off.